Welcome to Love Physiology and this video on how to standardise gas volumes. This is an important process to do if you're working with expired gas volumes, and this video talks you through the hows and whys of the process. There are two laws that affect the volume of a gas. The first is Boyle's law. This states that the pressure and volume of a gas have an inverse relationship. Therefore, if pressure increases, volume decreases, and vice versa. When collecting expired gas, the pressure of the environment can affect the volume, and this needs to be taken into consideration. You can see from the figure on the right that as the volume is decreasing, the pressure in the container is increasing. The second law is Charles's law. This states that the volume is directly proportional to temperature. So as the temperature increases, volume increases. Therefore, the temperature of the environment or gas is also important to take into consideration. If the laws are ignored, then the gas volumes will be incorrect. Here are some key terms that are useful when standardising gas volumes. Firstly, ATPS. This is the original volume of the gas and is affected by the temperature, pressure and humidity of the air. The second term, BTPS, is body temperature, pressure, saturated. This is used when someone wants to correct for the conditions in the lungs. Today we are not going to look at this term, and we're going to focus on the next term, which is STPD. This is standardised temperature, pressure, dry. This is generally the term we use when we're correcting gas volume, and we want to go from ATPS to STPD to show the gas is standardised. The corrections we need to make are to take into consideration the temperature, pressure and water vapour of the air we're collecting. So when we start the process, we are collecting the gas or air in form of ATPS, and no corrections have been made to the volume. And then we want to correct the volume to STPD. Therefore, we're standardising the temperature to 0 degrees centigrade, standardising the pressure to 760 millimeters of mercury, which is standard sea level pressure, and we want the expired gas to be dry, so there's no water vapour or humidity in the air. When we want to correct the pressure, sometimes it can be measured on a barometer in millibars or hectopascals. Now, to correct this to millimeters of mercury, we just multiply either of those values by 0.75, and that will give the value in millimeters of mercury. Sometimes people get confused and they use the millibar or hectopascal values, and that will not give the correct calculation. This is the equation for converting ATPS to STPD, and in a minute we're going to work through an example of how to complete this equation and standardise gas volume. Just to note that one of the boxes relates to temperature. That's where you can see 273 divided by 273 plus T, which is temperature. This number 273 comes from the thermal scale called the Kelvin scale. This is a scale where there's absence of thermal energy at 0 Kelvin. If you look at 0 Kelvin, that equates to minus 273 degrees centigrade. Therefore, that is where the number 273 comes from on the equation. You don't need to know any more than this, but it's interesting to find out where this comes from. Now we're going to work through an example of how to standardise gas volume. The example here shows a UK student is undertaking a VO2 max test, and their ventilation at rest is 6 litres per minute. The barometric pressure in the lab is 750 millimeters of mercury, and the temperature of the gas is 23 degrees. We're going to work through the formula now and see how we can standardise that gas volume of 6 litres per minute. As you can see from the equation, we're filling in some values. So we want to get to VSTPD, but to do that we need to correct the gas volume of 6 litres per minute, and we need to do certain things in the equation to actually complete that. In the first brackets, you can see that we filled in some values. So the first one is PB, which is barometric pressure, and that is recorded as 750 millimeters of mercury. Then we're minusing pH2O, which is water vapour pressure. Now that number is 21.1. I'll show you in a minute where that value comes from, but there needs to be a table where we get that value. So that table comes in a minute. Then we divided that bracket by 760, which is the sea level pressure which we're standardising to. The second set of brackets involves temperature. So you've got 273 divided by 273 plus temperature. The temperature in this example is 23 degrees. Therefore, that is what we put into that set of brackets. Now, the next stage is going to be to calculate the values from the brackets in order to get two correction factors, which we can use with the 6 litres per minute. Here are the correction factors. Therefore, you've got 6 litres per minute, which is the original volume. Now, this volume would be the volume of gas collected, likely in a Douglas bag. And then you're timesing that by the two correction factors from the brackets. The first one is 0.9590 and the second correction factor is 0.9222, and they're taken directly from the brackets. The final stage is to times the 6 litres per minute by the two correction factors, and doing that you get a value of 5.31 litres per minute. Now this is the standardised gas volume. As you can see, it's slightly lower than the original value. If you're getting a value that is far from the original value, then you're likely to have done something wrong in the calculation above. So you'd have a look at those values to check it. But it should be usually slightly lower than the original value. I'm just going to show you now how to get the water vapour pressure, because that's the value we still haven't got from anywhere, which was 21.1. Now the next slide will show that. I mentioned earlier that we need to get a value for water vapour pressure, or pH2O, and this is an example of a table where you can get that value. To use the table, all you need to know is the temperature of the gas, and you can read off the value from the table. So as you can see on this example, we're looking for 23 degrees centigrade. What we do is go along to 20 and then down from 3, and we get a value here which is 21.1. Now that is the value which we used in the original equation. So the water vapour pressure of 21.1 millimeters of mercury is what we're using in this example, and that's what you can see in the previous equation. So in summary, gas volumes are affected by temperature and pressure, and we've looked through the different laws that control this. So it's very important that volumes must be standardised to compare with other measurements. This would be, for example, if you want to compare with your results from a different day, a different lab, a different country, has to be standardised. Otherwise, there's no comparison between values. And converting from ATPS to STPD requires a simple equation and correction factors. We've gone through that example today, and I suggest if you need to go through your own example, you can work through it with your own values, and then you should come out with the correct standardised gas volume. Thanks for watching, and I'll see you in the next video.